Hey everyone, I'm Shriram Balaji and welcome to my talk on Rust Unlinked, a journey through Rustc, symbols, linkers, and static libraries. So I work at Microsoft in the Microsoft 365 core team, and I have been tinkering with Rustly roughly around since 2020, doing some minor open source contributions. At Microsoft, I've worked across the stack on things like Outlook, mobile, contacts, but right now I work on a large orchestrator service that is responsible for handling trillions of events per day across different Microsoft services. At Microsoft also, we've started slowly adopting Rust specifically inside the Microsoft 365 ecosystem, and it's starting to gain a lot of traction right now. I have been starting to read a lot more about databases, systems programming languages, and distributed systems. And I'm at Shriram Balaji almost everywhere on Twitter, LinkedIn, GitHub. And so feel free to hit me up wherever you like. So that's enough about me. So what's the agenda for the talk? So the main thought here is to understand a little bit about linking. We'll get to why understanding linking is important a little bit down the line. We'll take a high-level overview of the Rust compilation pipeline. What happens in an object file? You might have seen an object file. You might not. You might already know what it is. So we'll look at what is inside an object file. We'll understand the ELF format, which is the format in which an object file is present in Linux and Unix systems. And we'll look at symbols, symbol tables, and static libraries. I will get to static libraries and cargo build scripts at the end. And as we go through you'll have a lot more clarity as to what happens in each step. Right, cool. So let's understand linking, right? So what is linking? Linking is effectively, it involves combining object files into a single executable, right? Or it could be a shared library. You can think of it as putting a puzzle pieces together to create like a working program, right? On Windows, you'd get, when things are put together, you'd get an executable which is a .exe. On Mac OS and Linux, you would effectively get a program which is an ELF file, or on Mac OS, you'll get a Mac O file, executable with the plus X flag set, right? So that it can be executed. But in linking, the important thing is something called a symbol resolution, where the linker effectively matches variables, function names to the specific memory addresses, making sure that everything fits together, right? Just a note on the symbols. We'll get to what symbols are and looking at actual symbols in a working program later in the talk. But just baseline understanding we need to have is, you can think of symbols as the variables, identifiers, and function names, right? And how they map to just the memory addresses. So that if you're, for example, if you're calling an external library, the linker's job would be to find this particular symbol from another library, and then make sure that your code is able to map to that particular shared library code, right? Something like that. Okay. But why is understanding linking even necessary, right? At least in the context of Rust, a lot of the heavy lifting is already being done for us, right? For example, the cargo build system already does a lot of it for us. And without us having to even think about these object files, or without having to even think about any of this, Rust will compile and give you a working static executable that you can effectively ship anywhere, right? But it is crucial to understand that, because linking time is actually a big part of compilation, right? And if you've written Rust, or if you've heard, one of the biggest complaints of Rust by people is compilation time, right? The Rust compiler team has been doing a phenomenal amount of work in terms of getting the compilation to run faster. But it is even today in large projects, right? Roughly half the time could be spent just in the linker. Just a case in point, there's this project called grep, or RG for short, is a project that you can think of is a much faster grep command in some sense, but it's actually a much faster search command and search CLI tool. And if, a popular use case for the RG is something in VS Code, right? So VS Code uses the ribgrep to actually go and search for, if I remember correctly, if you do a search all occurrences of a particular thing, it uses ribgrep internally, if I remember correctly, right? But so the point that I'm trying to make is, understanding linking is important because it can eat up a lot of your compilation time, right? So if you know your compilation is taking longer, it is a good way to understand why it's taking longer, right? But before we get to the linker, right, we'll have to go through compilation, because the linker is the last, almost the penultimate state, if you think about that, right? It's the state right before you get the executable, right? Before that, the code has to be compiled, right? So the main phases of the compilation are, the compiler compiles source files into object files, and then the linker takes all those object files and then compiles them into a single executable or a shared library, as we saw earlier, right? Okay. So, but there's something called static linking that Rust prefers, right? Why is that the case? So what is static linking is, I'm sure you already all know, but so the static linking is where all the necessary dependencies are compiled, and then the final executive binary, everything is present statically, right? As I was saying, you can easily enable it enables easy distribution, but the bigger problem is that since everything is, it's effectively pulling everything into it statically, the executable size is much larger, right? Dynamic linking allows a program to load all of these external libraries and shared derivatives into memory and use their functionalities at runtime rather than at compile time, right? If you use C and C++, it usually prefer dynamic linking, but whereas Rust, the more obvious preference is static linking, right? But before we get, so for us to even get to linking, we have to have a cursory understanding of Rust compilation, and that's what we'll try to do. So just a quick disclaimer is that I'm not a Rust compiler dev. Rather, just I'll go through this as in the lens of someone who's curious about Rust compilation, and then just happen to go through and understand and read through some of the Rust compiler code. I do not particularly claim to have any authority in terms of my compiler internal knowledge, but rather just sharing what I have learned in the course of writing this. I wrote a blog and then the talk. Okay, so the high level overview here is again very simplified. Everything is presented for clarity. When I say linearly, is every step in the compilation pipeline is presented as one after the other. But in actuality, that might not be the case, because the actual implementation as of today from 2021 is the Rust compiler is moving to something called as a query-based compilation model. So what the linear model is called as a path-based implementation, where everything, as I mentioned, is everything happening linearly. But I'll talk about what is query-based compilation after this, right? Okay, the first step is lexing and parsing. So let's take this simple source code, which is just a main function which has a println macro and which just prints hello world, right? After that, so the first step is the lexing, parsing, and code analysis and optimization. I've just put together all of these steps into one, but these are individual steps on their own, right? So what happens first is the lexer, right? So the lexer operates directly on the input strings, in this case, whatever is the source code, and then produces simple tokens, which are effectively a pair of like type and tag, right? Saying this particular type of a token and it has an associated tag with it, right? But this token that is produced by the Rustc lexer that we see here is not directly parsable, right? So there's something called as a parser, but it is not directly parsable. It does not have enough information in it. So what the Rustc parse lexer, there's another lexer over here, which converts the actual strings into parsable token types. So after that, the parser takes the stream of tokens and then turns them into a structured format, which is easier for the compiler to work with, which is called as an abstract syntax tree, right? So most compilers work in this where you have an input stream of tokens. There's a lexer that takes in these input tokens, that takes these input strings, converts them into tokens, passes it to a parser, and you get an abstract syntax tree. And the AST representation is the primary data structure through which most of the compiler internals operate with, right? Or at least it's the most highest level abstraction, after which there is the further there's a further optimization on top, so either on top of the AST itself, or you have some minimal representations of the AST in different format for the compiler's internal purposes, right? So the AST mirrors the structure of a Rust program in memory. It is an in-memory representation, and it uses something called as a span, right? A span, you can think of it as it represents a region in code. So if you have a block in code, it represents a region in the source code and provides information about where that source code is available in the syntax. So let's say you have information like line numbers, but you don't particularly have line numbers. You'll have the vertical and horizontal offsets in that particular file. Now, as to what that particular this println macro that we are seeing here, right? So where that is present in code, right? So all of that information is present in these structures called spans, right? That link a particular AST node back to its source. So you can think of a span as a mapping between your abstract syntax trees node to the actual source code text. Okay. So the next step is code analysis and optimization. This is pretty huge to grok in the sense that there is a lot of things that happen, and as I mentioned earlier, that all of this is very simplified, and I'm trying to, I might oversimplify a couple of things here and there, but this is just so that this talk, we concentrate a lot more on linking and rather than understanding a lot more about the compiler internal, right? So the ASC is now then further loaded into something called as an HIR, right? A high level intermediate representation, which is an internal representation for the Rust compiler to work with, right? So this concept of converting a higher level tree into some other internal structure is called lowering. And during this lowering, Rustc does a couple of things. It's like it it expands macros, right? Like for example, the print line macro, right? You can think of, I'm sure you all know what a macro is, but just for brevity, so in this case, right, you can think of this as a macro as effectively replacing this macro call with the actual definition that is present inside the standard library, right? I do not want to particularly get into details of what hygienic and non-hygienic macros are, but a high level look at what a macro is that's what that is, right? It also desugar syntax. So if you have if-led syntax, it converts that into a match expression, right? And it performs name resolution. For example, if you have a module import or if you are importing macros, all of the resolution of what that points to happens during this lowering process. So after lowering into a HIR, the HIR is where the main couple of things happen, which is type inference. So let's say you have a code that says let a equals 20 or something like that, right? So it needs to have, by default, it will, I think as of today, it will infer this as a 32-bit integer, right? So that is a type inference where we do not explicitly specify that as a type, explicitly specify a type there, but is able to infer that this is a 32-bit integer, right? And trait solving. So for example, if you have it helps identify the correct implementation of a trait for a particular type. So if we are implementing a specific trait for a given type, we need to identify which of that happens, which of that is the correct one, all right? So all of that happens with the HAR. So that the compiler then runs type checking. So type checking is, you can think of it as converting whatever the types that you found in the HIR, which is the previous step, and then which is converted into an internal representation of the type for the compiler. Like say if you have a function that takes in, let's say it takes in a specific generic, right? And then you also have a self of that particular generic, self : generic, right? So in the HIR, you will have this represented twice, right? So that particular trait is being referred to twice in the HIR, but after type checking, you know that you're actually referring to the same trait. So you don't need multiple copies of that trait. You just need one, right? And that is where you have, you do all of that type checking and you get something called the typed HIR, which is THIR. Which is again even fewer. We have to learn a lot more optimization on top of this to even get to a point where you can get anywhere closer to an executable, right? So that is why we have multiple steps, and in each step there are different things that happen, different phases that happen, different stages that happen, and each of those stages will effectively be an input to the next stage in some sense, right? In the MIR is where your borrow checker actually kicks in. All of the borrow checker rules come in the MIR, right? And all of the rules that of the borrow checker that we already know are checked in this particular phase, right? It also does something called operator lowering. Like for example, let's say you implement your own add operator or something like that, right? So it needs to call if you implement add on your particular specific types, right? So it will need to call the exact particular function method that is responsible for that particular add operation. Operator lowering happens there. Monomorphization, which is a fancy term for generating specialized code for each type, right? So it is effectively, if you, let's say for example, you have a function that takes in a vec of t, right? And your actual code actually just uses a vec of 32-bit integers, vector of 32-bit integers. So after monomorphization, instead of your code having a generic t, the MIR will already effectively replace that with something that is a vector of 32-bit integers. This is done so that there's a lot less ambiguity in terms of identifying the right method for that particular specific type in runtime, and rather in compile time, we've already done that, right? This monomorphization is popularly known as one of those zero-cost abstractions in generics, because effectively what we have done here is we've removed that ambiguity for the runtime and then moved that over to the compile time. But again, if you think about it in some way, as if you overuse generics, this is effectively going to take a hit, right? So the compiler is going to spend a lot more time doing monomorphization, and there's never free lunch, right? So whenever we even if we say that it's a zero cost abstraction, it's not technically zero cost because the cost is most likely going to be paid in compile time, right? Okay, enough about that. So let's get to the next step. So we've up until this point, we have something called as just a quick recap. We took from lexer, gave tokens, got an AST, from AST got an HIR and then an MIR, right? So we right now have a middle level intermediate representation. So this MIR is effectively needs to get ready for the code generation step. By default, Rustc uses LLVM for code gen, right? And hence the MIR is then converted into LLVM IR or LLVM intermediate representation. This LLVM, if you already don't know, it contains a modular reusable pluggable compiler backend that is used for compiler projects including Clang, C compiler, and Rustc and a lot of things like that, right? But it's also used by Swift Swift, and it is Chris Latner, who's the founder of LLVM, is an incredible engineer, and they've also launched something called as a Mojolang very recently. But the LLVM project is a much large project, and a lot of different compilers are usually being written on top of it, right? Okay, so have a note of this LLVM IR. We'll try to look at, if you have enough time, we'll have to try to look at what an LLVM IR looks like, right? Okay, what do we have finally? We have an LLVM IR, right? This is what is going to actually generate the executable. So what Rustc has done is Rustc is now what is called as a compiler front end, right? And LLVM IR is what is called as a compiler backend, right? And the compiler backend's responsibility is to actually generate the final executable that you see, right? The reason that most compilers work this way, a lot of modern compilers work this way, is because once LLVM is able to take this, right, supporting a new platform becomes much less trivial. Because let's say we introduced WebAssembly, right? Just because Rustc was already using LLVM, the Rust compiler was already using LLVM, it was much easier to add WebAssembly as an output format on executable, because once LLVM added supported for WASM, it was much less trivial for C to do it, because it's an output format, and Rustc does not particularly need to care about it, because as long as it gets converted into an LLVM IR, it's going to get converted into a final executable or whatever the format is, right? Okay, so as I was saying, so it gets converted into LLVM IR, it gets converted to something called, it's like an assembly, right? And then from the assembly, you have a links to the object files, right? And these object files, LLVM IR, if I didn't mention earlier, it looks like assembly. It has additional low-level types and annotations, but it's not actually really human readable. LLVM performs a lot of these optimizations and spits out the object files, right? These object files are passed on to the linker. On Windows and Mac OS, they're using the systems linker, but as of May 2024 in Linux, it's passed on to something called Rust LLD. So Rust LLD is effectively LLVM's linker, internal linker, and thus using the LLVM, leveraging the existing LLVM toolchain even for the linker is an additional step, because that means you have a good guarantee that this works well. And instead of historically, some older linkers on Linux platforms have had issues with linking time, and I've linked to the actual blog post where they've mentioned this particular change in Nightly. And after this change, they have seen a drastic increase in terms of drastic reduction in terms of the linking time in Linux builds. Okay. So after all of that, the linker then links together everything and then the object files, and then you have packaged that into a nice looking executable. Perfect. Okay. This is a quick detour, right? So we talked about all of this, right? And we went through all of this to understand that, and understand every step of the compilation model, right? But actually what happens in the compiler today is something that I want to touch upon a very little bit, right? Why is because you might go look at the Rustc code today, which is what I did, and then be slightly surprised that it is not exactly the way that it is. Not all of the Rustc implementation is parse-based, and everything, a lot of that is moving into these queries, right? So what are these queries? So a query is effectively a way for asking the compiler questions about itself, right? So you can think about this as, when we use the term compiler DB, right? So this, you can think of this as a representation of the compiler's knowledge about a specific crate. I'm sure you know what a crate is, right? So every crate information, that the compiler has some information about that particular crate, and there is the job of that query is to query that particular compiler's database and then get some facts about it, right? So for example, it can ask how many lint rules are there, it can get the HIR, get the MIR. So each of these are queries, right? And a query it must know how to compute its results from that compiler database, even if it does not have it already, right? But usually a query will have a name, a key, a name which is effectively an identifier, a key mentioning what it is querying on, what to actually look up, a result type that is specifically of what is the kind of result it wants to yield. And I think that's obvious. There are query modifiers to make some changes to the query, and a provider function. So a provider function is effectively the actual implementation saying that specifies how the result can be computed if it is not already present in the compiler database, right? So the compiler database, as I mentioned, is an internal representation of the knowledge of the Rust compiler that has on a specific crate, right? Or on a list of crates, or on all crates for that matter, right? So if it's not there, if that particular information is not at the database, it's the responsibility of the provider function to tell how to actually compute that information and then save it. So we'll see, we will also memorize all of this information, right? But if you remember, all the steps that we saw from earlier it's modeled as a query, right? And if you let's look at a very quick example of what a query itself looks like today from the trait solving step. If you remember, we used the HIR, the high level intermediate representation, to resolve what the exact trait looks like, right? So this is again a snippet from the compiler source code. That there is something. This is what is called as a query definition, right? I'm not particularly going into the details of this because one, I don't have a lot of knowledge. This is mostly based on understanding that I have, and two, it is not particularly in the scope of this talk to actually go into how the query implementation looks like. But if you squint a little bit, so what is this actually telling? A query is the keyword, right? The query name here is the implementations of state, right? If you remember a couple of slides back, but I was talking about all of the things that comes up in a query, right? And the query key type here is a create num, and a def ID. I think some context is required here. So the def ID it identifies a particular definition, right? So it is composed of a create num, which is identifies the definition comes from. A create num is basically where the definition comes, which crate the definition comes from, and a specific index, right? And here the result type is a TCX. So TCX is an internal representation of the type. It is effective. Think of this as a context for an internal representation of any type. So if you have a type for an I32 or a U32, that is, the Rust compiler has its own internal representations of all of these types. And for each of these types, the compiler will create something called as a type context, right? When the query is run, the compiler gets all of, in this particular case, right, for this particular query, what is the result of this query is compiler gets all the implementations of the trait, and then what it will effectively memorize it, right? Given a specific crate and create num and the definition ID, this particular query is going to get all the implementations of a very specific trait and then save that together and then put that in a central place, right? So what is going to happen is the next time the same query comes with the same key, it's going to come back from the memorized results, right? Instead of directly going to the compiler database, right? Typical memorization strategy. Memorization enables something called as incremental compilation. You don't have to recompile all the crates, but rather if the crate has been compiled and some of the results have already been memorized, instead of going and recompiling and looking at the compiler database, those results will be reused. So that's how you have something called incremental compilation. All right. I think we spent a lot of time, roughly 20 minutes in understanding compilation. But what we actually want to understand is linking, right? We spoke all about this compilation, but what we want to look at is linking, right? What we want to understand is linking. So you might have looked at a .o file in the past and then wondered, right? What are these files, right? So the Wikipedia definition of that is an object file. It contains machine code or byte code. It can contain data and other metadata that is generated by a compiler or assembler during a compilation process, right? The machine code is then generated. Whatever the machine code that is generated inside the object file is known as object code, right? But so if it's just machine code, right, can we actually put together all of that ourselves? So that's something that we're going to try. But the catch here is, if you've already done this in C and C++, this might not sound like something that is difficult to do, right? In dynamically linked languages, this is far more straightforward to do. The experiment or the learning that I had was to trying to replicate the same thing in Rust, right? If I try to manually compile some source code that depends on some other source code, right, and manually try to link them using the object files, how feasible it is, right? So that is what we're going to try. Okay. So let's look at an example, right? So we have a foo.rs on the left and a bar.rs on the right. What the goal of these two files is, we import a global variable from foo.rs in foo and in bar, and then it updates its value to 20, right? So there's a global variable which is initially set to 5, right? And then that in the foo file and in bar, we basically take that 5 and then mutate it and update it to 20. That's a simple code, right? Some context on what the code is actually doing is, right, the no mangle attribute that we saw, it disables something called mangling. When you write Rust code, it is compiled, identifiers are mangled, right? You can think of it as jumbled in some sense, right? And it is transformed into a different name altogether, right? For example, the global variable gets mangled into this gibberish looking text, right? So why is the main reason that this is done is so that when you have all of these names you have global identifiers, right? So you don't want them to conflict with when you're linking with other libraries, you don't want them to conflict, right? Let's say I have a global variable, a variable called global declared over here, and some other library has a global declared here. If both of them try to use the same name, that's going to be something called as a name conflict. When the linker does symbol resolution, it has a way of identifying how to resolve them. But despite that, it is better to actually mangle them so that you don't end up with any of these conflicts, right? So we specifically we are disabling this with no mangle so that we can visualize these symbols, right? Again, I'm kept repeating the term symbols, hoping that it already made sense, but even if it hasn't yet, it'll make sense in a quick second. So what is effectively happening here is that as I mentioned, we have an extern C that the extern C block is telling the compiler that there is a global variable defined elsewhere in a foreign library, right? For bar, the foreign library is foo. And when you say extern C, doesn't mean we are interoperating with C, but rather we are using the platform C ABI, right? ABI here is application binary interface, right? So what that effectively means is bar is assuming that a variable declaration for the global variable exists somewhere, right? And this particular piece of code is unsafe because we are updating a global static mutable, right? And that is, why is that unsafe? You can think about it for a second, right? That is obvious. But rather the unsafe call on the right might be something that you might want to understand a little bit, right? So this block is unsafe because Rust cannot guarantee safety in FFI calls, right? We are trying to mutate a global static variable imported from some other library, which obviously cannot be memory safe, right? But if you think about it that for a second, C libraries often expose interfaces that aren't that safe, right? So if you are depending on some other functions that takes a pointer argument that isn't valid for any possible input, you end up with raw pointers that are dangling. You'll end up with dangling pointers, which is again falling out of Rust safety memory model, right? So that is why this block is unsafe, right? All right, let's compile and get those object files. So, but what I mentioned that we want to try to actually manually link and not try linking these object files. Like the goal is we have foo.rs and bar.rs. Let's not use cargo, but try to manually link these two together. Typically in C you would use GCC, which has which has an interface to the LD linker, which in Linux, and that would actually perform the linking, right? Can we do that ourselves is something that I'm trying to try. And that is why I don't want to use cargo for now. So what we would do is we can use Rustcs, and the if an emit argument will emit an object, and we are emitting an object for the foo.rs and bar.rs. So they basically compiles these two and then emits an object file, right? All right. So we spoke about object files, and then we said object files have symbols. But again, a definition of what a symbol is, it refers to, again, just reiterating, it refers to any identifier or a variable name or a function name that is stored in a data structure called as a symbol table, right? And symbols are stored in sections of the object file in a specific format called as the ELF format, right? On Unix, this is the ELF format. On Mac OS is the Mac O format, and on Windows, it's the COF format, which is common object file format, right? In this particular case, we're going to look at just have a very brief look at the ELF format, but let's actually look at these symbols, right? So there's this utility called as nm, right? And nm, the main goal with nm is enabling you to actually visualize, look at the symbol table in a specific object file. The object file itself can have multiple sections, which we'll get to in a quick second, right? We'll get to all the different other sections that are there in an object file, but we need to look at every symbol. That is, the nm utility allows you to look at least this is on Mac OS. On Linux, you will have something called read elf, where you can read the entire elf file directly, and that it has multiple options for you to just show the symbol table and do a lot of other things. But specifically, I'm using the nm so that just for the sake of simplicity on Mac OS, right? So the output of the nm command here, you can see that there is a global data section symbol, and there is a global text section symbol, there is a local symbols and uninitialized symbols, right? So here, if you look closely, right, so all the lowercase t, d, and s, those represent local symbols, and all the uppercase represent global symbols, right? And ltemp here is temporary symbols that are used by the compiler, but specifically, right, so here this text section has the foo function that we declared, and the data, right, the global variable that we initially set it to 5 and then muted it to 10 or whatever, right? So that is present inside the data section. So the text section has the references to the function name, and the data section actually has the variable that we are trying to update, right? So that's what we infer from this particular symbol table, right? If you look at the symbol table for bar, right, right now we have not linked these two files. Right now, both of these files have just been compiled, and then we are seeing the output for these two files, right? We are seeing the object, we have an object file or a .o file for these two, right? And then we are effectively trying to just look at what is inside them, right? We are taking a peek inside these object files and trying to understand or make sense of what is inside them, right? Specifically here, there is a U symbol that we didn't see earlier, which is an undefined symbol. Why is this a U symbol? Is because it is where the actual global symbol exists, right? So the in bar.rs, if you see from earlier, it was referring to an external global variable. We had an external block that said there is a global variable somewhere that the bar.rs does not know, right? And this particular, so since we have not linked foo and bar yet, right? So it is an undefined symbol. So and the object file does not have any reference to saying I don't know where global is, right? So bar saying I don't know where global is. You have not linked me to it. So for me, right now, this is undefined. So this is effectively a placeholder that says is undefined right now. And if you actually perform the linking together and stitch all of these two things together, this might actually resolve to your reference to a global symbol elsewhere. That is what this undefined is referring. And here the bar, as we were seeing earlier, right? So the text section here has the underscore bar, which is the function name, right? I think I think it's clear up until this point, right? Okay, we mentioned all of there's a lot of different sections in an executable file, in an object file, right? And in Linux and Unix systems, the format of how these sections are present is called as elf, right? And this is what a typical elf file actually looks like, right? So it will have a header, which is all the metadata for the object file. All the assembly language code, right, will go inside the text section. Read-only variables that will go inside the RO data section, like data, which is the dot data section, which we saw the capital D and the small d in earlier. So that is where the read, write, and global variables go in. There's something called as a block start symbol. BSS, it's effectively a shortcut to save. Say, for example, if we have a value that starts with 0, instead of allocating zeros in the object file directly, it's just saying that this particular symbol, it's just denoting that this particular symbol is initialized to 0. Right? So that's what BSS is. The symbol table that we saw earlier, right, like in the previous slide, right? So this is present inside this .symtab section, right? And so if I also mentioned that there are chances of having entries that are not already present inside the symbol. So if there might be symbols that are not present, right? So what the elf file will do is it will add these placeholders in these sections called relocation entries, saying that these are missing symbols, and this base effectively a to do for the linker saying that these symbols are not there with me, and it is the job of the linker to fix these symbols that are not there. So right now we have still not arrived at the linker, right? Just to be very clear, we have still not linked anything. We still have just object files, right? And effectively has all of these to-dos saying that it's your job to go fix all of these relocation entries. I don't know where they are. And for debugging, you use the stack, the debug line and str tab. All of these are used for specifically for debugging purposes. So when you use a debugger, it uses most of the symbol information that is coming from all of these debug sections are used, right? Okay. We went through all of that to actually understand that we now have object files that we need to manually link, right? Just so that we link them in a single file, we'll create just a main.rs that has an external C block, right? And what we are effectively saying is there is a foo function somewhere, there is a bar function somewhere, and there is a global i32 somewhere. So we want to call foo and then call bar, right? And then finally print the value of the global. So the goal here, what is effectively should happen is when you have foo and bar, that is running, initially the global value should be set to 20, right? After everything, after foo has finished and after bar has finished, the variable that was set to 5 needs to be mutated to 20. That's the goal here, right? Very simple and straightforward. So here we are doing the same thing. We are using the emit obj to compile a main.2, right? Okay. Great. So now we have a way to link all of them, right? Finally, we are at a point where we are at the linker. We are using the LD linker, right? LD on Linux machines, it's the de facto toolchain is GCC, right? And the default linker is LD. LD is again part of the GCC compiler. GCC, if you don't know, it's the GNU compiler collection. And here, when you call LD, right? So we are trying to invoke directly invoke the linker instead of using GCC. Just a note on macOS, the new default linker in macOS is called LD Prime. If you're on Xcode 15 and above, you have something called LD Prime, which is a much faster linker in comparison to the LD64, which is earlier, right? And this is a much more latest linker. And I think a lot of alternative efforts that went on to increase the link times in macOS have fallen off, and instead Apple has taken an approach to actually make a much faster linker for since Xcode 15, right? Okay, cool. So now when we try to manually link, we have an error that blew up in our face, right? So if you squint at the mangled error message, right, it seems like a symbol reference to core ops function ones call ones, right? So this particular reference is not there, right? So what is effectively happening is we tried to link. What did we try to do? We tried to take a main. We tried to link a foo and a bar into a main file, right? We have three different object files here, and then we are trying to link all of them together, where the main has references to both foo and bar, right? But what happened here is, since the standard core create needs to be linked here, right? Internally, when you have a main function, when you are implement your own things, after I found this after searching a little bit of online, that this needs to link the core create, right? But we can't just directly link the core create, because the standard core create is not an object file; it is an rlib file, and I don't think there's any direct way to actually link an rlib file, right? You can think about other ways, right? You can, in the main function that we saw, we could have something called as a no standard. You can say explicitly, you can add a no standard attribute saying that I don't want the standard library. Now, if you don't have the standard library, you need to implement your own panic handler. And if you need a freestanding library without you need a freestanding binary without a standard library, you would have to implement your own panic handler and all of that, which I don't think that's particularly necessary to understand, right? I don't think that is at least for the purpose of this particular talk, or even when I was writing a blog post on this same topic, it did not seem right. So I didn't want to actually go through the hassle of writing my own panic handler implementation, because I'm not particularly keen on having my own freestanding binary. The goal is to just understand linking and seeing if I can link all of these individual files together. All right. So what does Rust actually have for us? There's something called as a static lib, right? So we can usually when you have a hello world project, right? When you have a hello world project, the Rust compiler will default to a bin or a binary, or if you specify a library, it will create if you have a main.rs, it's going to be a binary in most which is going to get you an executable, and a lib.rs if it's going to be a library that you want to share, right? These are the main things that will happen, right? But there is a specific create type called as a static lib, right? Instead of actually trying to link the core create, we can use this particular create type, right? And then use Rustc and then say, I want, ask it to actually compile these as a static library. So what will happen is you will have a foo and bar, that are compiled to static libraries. And then from those foo and bar, we can actually link them together using cargo, right? So the output, if you see, is a .a file, right? Which is a static library or an archive in most Unix systems, right? And if you're wondering what happened to the .o files, right? So the .o files are there, the object files are there, but they're just inside you can think of this as just as an archive, right? You can think of this as like a tar gzip or a zip file, right? In some sense, right? So a .a is an archive file, and inside archive you can see all of those .o files that we saw, right? But if you squint, you can see that those files are not directly with the same name. They have an extension called .rcgu, right? So the rcgu in this sense, it stands for Rust Code Gen Unit, right? So if you remember from our compilation earlier, we were talking about this code generation phase. It is a unit of code that the compiler generates during the code generation phase, and that's what is called as that is why it has an rcgu extension to it. Again, that is my understanding. If you want to actually look at the just to make sure that things are okay, we can use the AR command again. If you add a -x argument, and then we can extract the actual object file, and then once we can call the nm command again. Once we call the nm command again, we can see that the symbol tuple is there. So what has happened is we're able to use the static lib create type, and then get the object files packaged into an archive, right? Into a bunch of archives, and then now we are going to link them together, right? But we missed cargo along the way, right? We've done a lot of these things with Rustc, and then cargo technically does all the talking to Rustc, right? Cargo is as a package manager. Cargo as the tooling, the build system for Rust is phenomenal. And that is how we should ideally do it. And the whole reason why we didn't do that is because we didn't want to be we wanted to circumvent it and directly compile it ourselves. But that is not the ideal way, right? So that is the learning here. So we can add a build script in the build script called build.rs in the project's root, right? And what we are doing here is we are saying we have these instructions in the build.rs that's saying that there is this folder called target/out, right? In this folder, look for a static library called foo, and look for a static library called bar, right? And then it tells the compiler to link those two static libraries together. There are other ways of that. There's something called as a hash link attribute if you want to add that. If you add a hash link attribute, you would also if you had a hash link attribute that is effectively a replacement or an alternative to this particular approach. All right, we saw all of that, but we didn't check what an llvm is. This is just a quick bonus. I am going to just quickly open my editor and show you what so these are the files that we talked about earlier, the foo.rs and bar.rs. Just in the build script that I showed in the previous step, right? There are a couple of other things that we are doing. Here is the commands that we are running, the Rustc, create, type, right? All of that we can put inside the build script. So we are using cargo to actually run the Rustc commands ourselves. So what we are doing is we are using the Rustc commands, compiling the foo and bar files into archives, and then we are instructing the compiler to link them together. That's what is happening in the build.rs. Okay, so to get the actual right, so this is what the llvm IR for foo.rs looks like, right? Again, I'm not particularly an expert in terms of LLVM IR itself, or not even an amateur at that, but this is sharing my understanding of what it is, right? This looks like assembly in some sense, right? But what the main areas here is, what is happening is here on line 6, we are declaring a global variable, which is we mentioned that is an I32, right? So it is declaring a byte array for 5. So what it is effectively doing is creating a byte array of 32 bits and then storing the integer 5 there. So what we saw in foo.rs is we actually had a global, this is that line. So let me split the editor. So I think it's a lot more clearer right now. So where we can look at, if you want to draw parallel, right? So what is happening is we are declaring an I32, and it is initialized to 5, right? And then this is the actual function where the foo is happening. So what is happening here is we are storing a particular pointer with this. We are storing a 32-bit integer called 10 in the pointer pointing to the @global reference. So @global here is the reference, and we are saying that what we are doing is we are saying the global needs to now be a global variable now needs to be updated to 10. Right. So that's what is happening here. llvm also has all of the information regarding the file name, the target platform, and all of that. But yeah, so I think all of that is not particularly necessary for us to understand. And so local, if I read correctly, if I remember, I think it's for a reference to a local function. But yeah, don't quote me on that. Yeah, that's what an LLVM IR also looks like for foo.rs. So that's mostly it. That's my talk. And I will share all the references to this particular talk. So there are some phenomenal talks. One of my main understandings from this is the Rust Borachecker by Neil Chamberlain Harrington was an introductory to the Rust compiler itself. And you can look at the Rustc guide for if you are interested in how Rustc does things, and if you are interested in contributing to Rustc itself. Right. And I think all of these links are really good to understand and read through. If you want to create your own operating system and create Philip Opperman's course on creating a Rust operating system in Rust without a standard library and a freestanding binary is a really good read. And Matt Godbolt, if you know godbolt.org is a really good website where you can visualize and look at look at a particular, put in a piece of code and look at the assembly and do a lot of things with Godbolt that I don't obviously know a lot about, but at least from my cursory understanding, I've used this and I found it to be very useful. So Matt's talk on the bits between the bits, Matt talks about a lot of other tools like object dump. There's this tool called object dump where you can actually visualize, look at the assembly for a particular object file and all of that. So I think that's a really good talk to watch. But other than that, thank you, and looking forward. Hope you have a great conference day, and yeah, looking forward to having. If you have any questions, feel free to reach out to me on Twitter, LinkedIn, anywhere. So thank you.